Hi, my name is Shragarthoid, and today I'll be talking about the development of gradient drift and Kelvin-Helmholtz instabilities in sub-auroral polarization streams. And I'll also be discussing a model that I have developed that allows us to look at these ionospheric turbulence generation mechanisms at much greater details and much smaller scales. And it's general enough to be able to be used for other ionospheric applications. So firstly, what is a sub-auroral polarization stream, or saps? They're characterized by a poleward electric field which drives a westward plasma flow, and it's typically associated with an ionospheric trough. So for example, from Foster and Burke, we have some Millstone Hill radar data showing a region where we have higher velocity and lower density. And then if this is important for morphologically, because this geometry is important for the instabilities that we intend on examining. If we zoom out and look at this from a more poleward perspective, in this polar plot on the right, from Lin et al. Is a global MHD simulation of the St. Patrick's Day 2013 storm. The black outline is the SAPS region, and we see that it has a very large longitudinal extent, typically in the dusk to midnight sector. And for my work, I'll be focusing in on the poleward wall of the SAPS, so along this wall over here. So in the SAPS region, there is a host of turbulence and ionospheric irregularities that have been observed. Below is an example of small-scale density variations from DMSP satellite data from Mission and Blaunstein. If we look here, the SAPS has been defined to be in this general region, and when we look at the delta n over n, we see that there's a whole bunch of density variations that exist here, but not necessarily outside of the SAPS. So there is something within the SAPS region that is causing these density irregularities to occur. And this is hypothesized to be caused by several different plasma instabilities. The gradient drift, the Kelvin-Helmholtz, the temperature gradient, and the ion frictional heating instabilities are all possible candidates. For this work, we were going to be primarily focusing on the first two, the GDI and the KHI. So the GDI is an interchange instability which is driven by a background electric field. In our case, we're going to be looking at everything from the reference frame of the neutral atmosphere. So the background electric field is driven by the neutral wind here, so in a manner such that E equals U cross B. And another requirement is you need to have a difference in the ion neutral and electron neutral collision frequencies. And what this does is this induces a Pedersen current. And then when you have a small perturbation in a geometry like this, for example, with a gradient, with a density gradient and a magnetic field and a background electric field, you get these small little pockets of charge that create these little tiny electric fields. And when you then take an E cross B drift of these electric fields, it causes the E cross B drift in opposing directions. This is how the instability grows. And the figure on the left here shows the condition for maximum growth, such that the gradient in density is parallel to the E cross B drift direction. And by nature of the way that the neutral wind direction is, this is hypothesized to occur at the poleward SAPS wall. The equatorward side is going to be such that we're in the stable regime of the GDI. So it's only the poleward side that's going to be the unstable regime. Now the KHI, now if we have a similar type of interface, but now consider on the left we have some velocity v1, and on the right another velocity v2. In our case, v2 is always going to be 0, but it does not necessarily have to be. As long as v1 and v2 are not the same, you have some velocity shear, you're going to have the Kelvin-Helmholtz instability occur, where the velocity is going to want to create these vortices, and it'll get the vortex-like structure of a classic Kelvin-Helmholtz instability. We have collisions and density gradients inherent in our model, and they provide damping effects to the Kelvin-Helmholtz instability. Because the Kelvin-Helmholtz doesn't particularly care about any of the directions of anything, as long as there's a velocity shear, it's hypothesized to occur at both SAPS walls. So the mathematical model that we have to assume that the plasma is quasi-neutral, so Ni equals Ne equals N, and it's an electrostatic fluid. We're only considering motion perpendicular to the magnetic field, and to deal with numerical error, we have artificial diffusion in the continuity equation. So equation 1 is our continuity equation, where we're only considering our E cross B drift as our primary driving factor. Equation 2 is our current closure equation, which includes collisional and inertial terms. An important thing to note here is we also have 2 additional equations evolving for temperature. We also have a few temperature terms showing up in the current closure equation. I haven't shown them here because they've been shown to be negligible and they haven't affected any of the work we have looked at so far. So what we also have done is we created a perturbed model where we split the variables, in this case phi and n, into a background and a perturbed quantity, a BG or P, as shown in equations 3 and 4. The reason for this is that when we look at the background conditions for saps, it's an inherently dynamic system. It is always changing. The issue is that it's changing much more slowly than the turbulence development that we have seen in observations, and so thus we would expect to see in our simulation results. The large-scale change is on the order of several hours, whereas the turbulence development is on the order of 20 minutes to approximately an hour. So what we wanted to do is basically make it such that the background doesn't change, and we could have just the perturbed quantities change. And another reason for this is so that we don't have to save a particular variable to be our equilibrium variable that we solve for. So what you can do is you plug equations 3 and 4 back into equations 1 and 2, and you get rid of anything that is purely terms of just the background. So the only things that are remaining are terms that are multiplied by perturbation terms. What you then end up having is an equation, for example, like in equation 5 for the continuity equation. You can do a very similar thing for the current closure equation. It's just more complicated, and I haven't shown it here. We can then solve this equation numerically. We discretize everything in space using a pseudospectral method. This is very useful because we have several nonlinear terms, and this very simply allows us to take our spatial derivatives and turn them into algebraic expressions. And what we then only have is ODEs and time. So one thing that we will need to deal with before we do any sort of temporal integration is how we actually get the time derivative term for equation 2, which I've rewritten here as equation 6. This dphi-dt term is not, we cannot easily just take it out and solve for it and get dphi-dt equals something. We have to first solve for it iteratively, and then afterwards, once we have dphi-dt, we can then solve for phi along with n and the 2 temperatures using a 4-stage, 4th-order Runge-Kutta method, evolve them in time. So here are some benchmark cases. First is the GDI, where on the left I have the number density, in the middle I have the x direction E cross B drift, and on the right I have the y direction E cross B drift. And we see some perturbations, and as we have things growing in time, what we're going to notice is, just by nature of the geometry, the perturbations on the left go away, but the perturbations on the right continue to grow. And that's just because the left is the stable side and the right is the unstable side. So we're capturing this physics correctly. And what we're even seeing is these hammerheads, these thicker structures at the end of these thin fingers for the GDI, are secondary Kelvin-Helmholtz instabilities that are occurring once the GDI has developed well into the nonlinear regime. So we're confident that we're capturing the GDI. Now, if we look at the Kelvin-Helmholtz instability, same exact thing. Left is density, middle is Vx, right is Vy. If we evolve this in time, we see some of the higher order, or the higher k terms damp out, but eventually we see some lower k terms develop, and we see a beautiful vortex structure that you would see in a Kelvin-Helmholtz instability. I turned collisions off in this case just so that we could have the instability develop very nice and quickly, and we could see the vortex structure. And we even see here secondary Kelvin-Helmholtz instabilities developing on the edges of the vortices. So we're confident that we can accurately resolve the GDI and the KHI. So now what do we want to do is to apply these to an actual SAPS region, and to pick parameters that are going to be more suitable for that and see what happens there. So for here, our coordinate system is such that x is north, y is east, and z is down. So we're assuming that B is purely in the z direction. We're not considering any sort of parallel motion to the magnetic field at the moment. So we take our plasma parameters to be for 300 kilometers in altitude. We have a gradient scale length, which is at 430 kilometers, taken from approximations from CEDAR. We have the neutral wind being at approximately 500 meters per second in the south direction, or negative x for us. We have an artificial diffusion of 10 to the 5 meters squared per second. And the parameters that I'm going to be changing in the 3 simulations I'll be showing next is the background saps velocity, which is westward in the negative y direction. It's going to be 3 things: 0, negative 100, and negative 1,000 meters per second. So the profile for the density and the velocity, I have the same exact profile. The only difference is the scales. For the density scale, we look on the left axis. For velocity, we look on the right axis. And this velocity will scale differently depending on which particular run that we are looking at. So now I have these preliminary results. If we look, I zoomed in specifically to the poleward region so that in each individual plot, the left part of that plot is inside the SAPS region, so lower density, higher velocity, and the right side of the plot is outside of the SAPS region, higher density, zero velocity. So on the left side is at the background velocity equals 0. So this is a purely GDI case, and it looks pretty much like the GDI what we saw before. We are seeing, maybe some of the hammerhead, some of the beginnings of the nonlinear effects beginning to happen for the GDI. And then once we include the background velocity at a negative 100 meters per second, what we intuitively would expect is that if you have on the left there's some negative velocity, on the right is 0, you would just expect there to be some sort of tilt as things start growing. They're going to grow in one way and then they're just going to get pushed along with the rest of the velocity. And that's exactly what you see. So far everything just makes intuitive sense. But then if we increase the velocity even more to negative 1,000 meters per second, we see that the actual magnitude of our perturbations, while we can still see the perturbations, the magnitude is significantly smaller. And there seems to be some sort of stabilization happening as we increase this shear flow. And that is still things that we want to work on some more. So for future work, we want to continue exploring this possible shear stabilization of the gradient drift instability. There has been work done in the fusion community, primarily in Z-pinches, that looks at how shear flow can stabilize some of the instabilities for the turbulence that they see. And we're going to explore some of their work and see if any of it could apply to the ionospheric things that we are looking at. We also want to consider other parameters that might affect the instability growth. For example, the background neutral wind, which really determines how strong our gradient drift instability is. We also want to modify our collision frequencies, particularly the ionosphere collisions, because those are the dominant ones. And that determines basically how things are going to change with altitude. We also want to change the gradient scale length and the location and width of the velocity regions. And all of these are very correlated with differences in geomagnetic conditions. So we have a lot of different parameters that we want to play with and see how the instability changes with these parameters. We also want to analyze the stability criteria with the geometry for both of these instabilities working in tandem, not just separately. We want to compare our results with turbulence spectrum we get from CEDAR. If you have any questions, please feel free to email me at trogr@vt.edu and visit this website if you want to check out any of my work or the work of my colleagues. Here are some of my references. Thank you for your time.